So welcome to the Ezra seminar today. I'm Semida Silveira, I'm professor in the Systems Engineering program, and it's my pleasure today to introduce Professor Tong. He is the Evan Joan Jacob Professor of Engineering at Cornell and the site director of the Power System Engineering Research Center. His current research focuses on power system optimizations, electricity markets, and AI machine learning technologies for power system operations. He received a bachelor in automation from Tsinghua University, and he has a PhD from the University of Notre Dame. He was also a postdoctoral research associate at Stanford University and a fellow of IEEE, and he was in 2018 Fulbright Distinguished Chair in Alternative Energy. So welcome very much. Looking forward to your talk.
Thank you. Thank you for being here. So I will talk about two generic problems, one being the probabilistic forecasting, in particular generative probabilistic forecasting. Second being anomaly detection anomalies, detection new trends. Both of them can be put under the general framework of AI foundation model. So I'm going to just briefly say a few things about the AI foundation model and why that's a important framework to tackle many practical applications that are not necessarily dealing with language. Okay, so a few things about it. Broadly speaking, so AI foundation model is a learning and decision architecture characterized by GPT, which means that it's generative and pre-trained. Okay. Generative means that it can produce sample scenarios that are beyond your training data. Pre-trained means that you can train a large foundation model and adapt that foundation model for various applications. This architectural design put additional requirements for what kind of applications will be suitable for something like this, and why this is a extremely profitable way to look at AI. I steal this picture about the AI foundation model. On the left, you have all kinds of data: text, images, video, equations, your published papers. They are used to train typically very large neural network. This part is done through the pre-training. Okay. What is most important aspects of a foundation model is that it can be, once it's pre-trained, it can be applied to many different applications. Answering questions, sentiment analysis, information extraction, having a private conversation with you, and so on. Okay. Now, why this particular architecture is so interesting? As you can see, that the amount of investment in developing a foundation model is growing in an incredible speed. $40 billion in 24, 25 is 25. In 23 is 25.2. In 22 is only 9. You can see this is so much money invested in something like this. Okay. Now, all the major players are in this game to build the foundation model as the primary engine for AI applications. Okay. You can find foundation model in all kinds of applications. Obviously, natural language processing, finance, medicine, agriculture, including power system. So this is extremely widely applied. you think why that's the case. Why this thing all of a sudden catch so much attention, and especially so much money get invested in this. The main reason is the following. Okay, my interpretation. It is a division of labor. Now, training a very large neural network is exceedingly complex. It requires enormous amount of resources. But everybody wants some kind of AI too. There's no one could have afford to build a very large neural network and train that neural network for each particular application. This division of labor allows the partition of an enormously expensive and complex task from a more application-driven tasks. Okay, so this pre-trained foundation model adapt to application, this particular architecture is indeed the right way to monetize these technologies. Okay. They will train this, they will send it to you, you do whatever you want. That's where monetization happens. Okay. Let me say a few key characteristics of AI foundation model. First thing, it has a generic architecture, what we call the autoencoder architecture. You take whatever the data you have, you train a huge neural network, you extract what we usually call the latent features that embedded in this large data set. And once you have this feature, this has to be essential features not for one application, but for all the possible applications you have in mind, right? And you have a decoder, and the output of decoder not necessarily perfectly reconstruct the original one. Nonetheless, it captures all the characteristics of the original data. Okay, this is the generic architecture of AI foundation model. So it needs to be pre-trained. It needs to be self-supervised, by which it means that you should not need to be labeled them. Essentially, this learns just from the data itself. Okay, whatever published work in the internet, all the videos, everything recorded, nobody's there to label them. It's to train by itself, right? And it must have a generative capability. That is, what's produced here, even though they're not perfect match of your training, it can be as many as you can get the data that carries the same characteristics. Okay, so the dominant way to implement this architecture is the so-called large language model. Okay, it has specific architecture. It has certain mechanisms embedded in this. That is pretty much all of the foundation model follows this particular framework. Okay. So far the most successful cases are in information processing, for example, behavior learning, probabilistic capture that can generate all kinds of fake data that you think, well, it's hard to distinguish, right? And then many others. Okay. Now, what I'm most interested in, not this type of application. What I'm interested in are more applications that coming from physical systems. Okay. I'm particularly interested in data that are time series, that has some causal flow that is generally happens in physical power system or physical system. Okay. So I'm interested in application real-time decision control, which means that in real time you observe what happens up to now, make decisions about future, and you have no access to what the future realizations are. Okay, most of these I'm interested in are physical system measurements, of course, can also be, you can embed other type of information as well. Okay. Okay, so I'm going to follow exactly the same architecture. I'm going to look for a encoder, a decoder. I'm going to take real-time data. I'm using, since I work on power system, I'm using all the power system data, measurements of current and voltages, frequencies on the power grid, the environmental measurements like wind, temperature, and so on, right? And also your past decision history. So those are the input of the encoder. Those are the things that you'll be used for training. Okay. Now, the type of applications that the AI foundation model. Once you train the foundation model, you're going to use that for different applications. Okay. The same latent feature will be input up for different applications. The detection problems, detection of anomaly, forecasting problem, estimating some signals that you cannot have access to, real-time decision control, planning, optimization, all these things can be put within something like this. Okay. Especially for planning optimization, if you're interested in potential future scenarios, the generative aspects of foundation model is extremely important because it can generate as many realizations as you want that match to the distribution of what you test here. Okay. All right. So that's the context of this talk. So it is perhaps better be described as a foundation model that are based on time series. Okay. All right. So the essential question is, what is this latent feature? You have lots of data, you want to extract this. You don't know how different applications are going to be used, so this has to be generic, but to capture the information or the characteristic of the input, but it also has to be much simpler. Right? It has to be much simpler. So let me describe the heroes in my in this talk. So Norbert Wiener and the Kallianpur in 1958 considered a version of this problem. Now, Wiener is a Cornell graduate with a degree of philosophy. But anyway, so in 1950s, so they considered the following problem. Okay. So suppose you have a random process being a stationary. Their question is, what will be a most efficient way to describe something like this? Okay. If it's random process, it can be arbitrarily complex. Describing this in the probability model is an infinite dimensional problem, right? So in the modern machine learning language, I'm going to explain what they were considering at that time in the context of autoencoder. Okay, so here is the input realization of that, and the Wiener and the Kallianpur has a big hypothesis. What they are saying is the following. So you put this autoencoder, and this will be the latent process. What they're hypothesizing is that for any stationary random process, this can be represented by an autoencoder where the latent process is ID uniformly distributed. Okay, this is quite a amazing simplification because all the samples are independent of each other. Each one has extremely simple distribution that is uniformly distributed between 0 and 1. Okay? This was referred to as the innovation sequence. Okay. Why do we call that as innovation sequence? Now, another important aspect is that the autoencoder and autodecoder are both causal, which means that it only takes past samples, not future ones. So this is a real-time operation rather than offline operation, you get a bunch of data. So here, the causal encoder and the causal decoder. So why do we call this innovation? You require these things being independent. So here, at time t, you extract a sample from the latent process, which will be a function of all the past. Okay. Now, because what they say is that the output of the decoder can reconstruct of the input, right? So that means I can replace these xt minus 1 with past innovations, right? Of course, I can replace all of them with past innovations. What you have is the innovation at current time is represented by the current input and all the past innovations, right? Now, this is independent of all the past, right? So that means this innovation realization captures the information in xt not contained in the past, right? So that's why these particular realization, particular random variable is called the innovation. It contains information only in the current, but nothing in the past. Okay, so yeah, only the new information. This is amazing. Yeah.
So the causal encoder is not a neural net here, or how is the innovation being done?
Being computed?
Yeah.
This is just a mapping right now.
Oh, I see.
Yeah, right now it's just mapping. There exists such a mapping. So mathematicians is only matters. There exists such mapping, right? Okay, so this is a grand hypothesis. If you can do this, this is quite amazing because it simplifies. It describes this random process exceedingly simple, right? But it is not true. It is true in many cases, not always true. So here comes another Cornell alumni, Murray Rosenblatt. He constructs counterexamples that this, for some random processes, such statement would not hold. In fact, these are not even weird random processes. These are actually quite common random processes. But he suggested an alternative. Okay. The alternative is that instead of insisting the autoencoder perfectly reconstruct the input, what he says, if you relax that restriction to make the distribution of the output of the encoder match the input. Mathematical term is that you want these two equal only in distribution, not almost sure. Okay. Significant relaxation. Okay. So we call Rosenblatt's relaxation a weak innovation autoencoder. Okay. So you still insist this to be highly uniform, but here they only match in distribution. This is not so good in certain application because if you say this is a great way to represent, if your application is to compress signal, this won't be too good. This won't be too good. Okay. Now, however, for inference problems, often all you need is the distribution information. We'll see why these, for certain application, it is all you need. Okay. All right, but as I said, how do you actually get this thing? How do you actually compute these two, the autoencoder and decoder? Now, there are only two cases that were known. Okay? One is the simple. Suppose you have a Gaussian process. If xt is Gaussian process, innovation is simply computed from the prediction error. So suppose I use if it's Gaussian process, if I use past sample to predict next, the best one, the optimal predictor will make some error, right? probably have seen this picture. So this is all the possible, this is the space spanned by the past samples. You want to predict the next sample. And the optimal predictor is the one that you choose this point that have orthogonal error, right? Clearly, when it's a Gaussian, when you have orthogonal sequence, they are independent. This is well known, so done by Homograph, Wiener at the time, also later by Kalman, including even non-stationary processes. The second case that's known is less obvious. Okay, so in this case, you could just do an optimal linear predictor, and the prediction error will be your innovation, and you can reconstruct it perfectly. Okay. The second case is not Gaussian. If it's not Gaussian, this is the only thing we know how to do. So if your process is not necessarily Gaussian, but additive noise is Gaussian. So this is called a white noise, additive white noise Gaussian process. Process itself is not Gaussian. Now, how do you get the innovation? You do nonlinear prediction. Okay. Take past samples, do nonlinear prediction optimally. That gives you the correct autoencoder that extract innovation sequence. But that's all we know. Okay, that's all we know. It's not clear how to use something like this until neural network happens. Anything we don't know, so let's try how to get it from neural network. Okay, so this is the input random process. This is the output of autoencoder. What we want is this being IID uniform, and we want to match these two either in realizations or in distribution. Okay, so that's not too hard to do once you put into the context, in the context of machine learning. So first you want to insist this being IID uniform. Okay, so it's easy to generate IID uniform sequence, and you compare these two. The difference of these two sequences, you use the error to update parameters. So this will be a neural network, will be implemented to enforce causality. Right? It's a convolutional neural network. And what about these two? All you need to do is compare them either in distribution or in realization. Okay. The rest of them you could just take all the algorithms that's developed there to train something like this. Okay. So of course you don't know how well the training will be. Not only that, one should be worried that in any practical applications, it is impossible to take infinite past samples. You can only take a finite block of past samples, right? So what's the effect of that? Suppose, so I'm going to describe what is the convergence aspects of this problem. Suppose all your neural network can only take finite past, from t to t minus k. Okay. For the encoder, when you do the training, also you cannot take infinite past. You take finite past, right? For decoder, you cannot use infinite past. You only use finite number of innovations, okay? And of course, by doing all these things, what we get is a fixed complexity of encoder and decoder, and also this training algorithm. You create something that is not necessarily innovation. In fact, it's less likely this will ever be a IID uniform, right? So the question then is, if you let k become larger and larger, how do these things converge to? Okay. As you can see, when k goes to infinite, you have this sequence converge. You can show that it converges to the true innovation, IID uniform, and you can show that the distribution of the output of the autoencoder will converge to the input. Okay. Assuming, for this thing to be true, assuming I'm going to train this optimally. My neural network is huge, arbitrarily large, I get the global min. In practice, of course, you probably don't. But theoretically, this is a sound architecture to implement something like this. All right, okay. So now I have the autoencoder, I have the latent sequence. How do I implement, rather than using a large language model, I call this innovation representation model-based foundation model representation. So I'm going to take all this data, and I'm going to train this to make innovation ID uniform, independent. I have the output of the decoder match the input in distribution. Okay. And I'm going to use, for different applications, the same thing. I'm going to first talk about the probabilistic forecasting, and then we'll talk about anomaly detection. The rest of things, we haven't done much. All right, so let me talk about probabilistic forecasting. Forecasting problem is you take the measurement up to T star. You want to know something in the future, what happens. So if this is your guess, we call that the point forecast because you try to predict what happens with a single value. Okay. Of course, in between, there are all kinds of things can happen. You have all kinds of realizations in between, and there is an underlying probability distribution that describes what the future samples will be. Right? To get this distribution is called a probabilistic forecast that captures the conditional distribution of the future given the past. I'm not interested in getting this distribution. It is extremely hard to do that. The generative probabilistic forecasting is one that generates realizations that follow this distribution. Okay. If I can come up with a way to generate different realizations of this distribution that happen to be correct, in principle, you can generate infinite many. You get something close to what it's supposed to be. But I'm not going to take the step, obtain this distribution, then do the generalization. Okay. So that's what I want to do. The generic structure of generative probabilistic forecasting goes like this. So this is what you have observed after time t star. Okay? You're going to do a mapping. You're going to take this information, produce a sample. But if you want to generate many, many samples following the same distribution, you need randomization as part of the input. Okay? So the design problem is the following. You want to figure out what is the mapping, and take the past sample, and some randomly generate the sample, chosen from certain distribution, so that what comes out here match what it should be. Okay, so these two things are what we're looking for. Okay, so that's how I describe, find the mapping H, sampling distribution so that what comes out has the correct conditional distribution. Okay, how do you do that? These are extremely hard. One way you can do is, okay, suppose the distribution has some finite dimensional parameter, Gaussian with mean and variance and so on, whatever distribution. Then the problem becomes relatively simple. Essentially, it comes down to estimating that parameters. But of course, you are restricted to that particular model. When it's non-parametric, when you know nothing about the distribution, these are essentially an intractable problem. Okay, you can think of why this is so hard. What you're interested in is a conditional distribution, condition based on the trajectory you have seen. But you only see one. You don't even have enough samples to get the second, right? So that problem is obtaining that analytical form of conditional distribution is almost impossible. I think it's almost impossible. Okay, all right, deep learning. With deep learning, you can do anything. You can just train something like this, somehow picking the right distribution, maybe you can get it. Okay. So my results tell you what they should be. Okay, I'll tell you what it should be. Now I'm going to use the innovation representation. Okay. So here is the innovation representation, the autoencoder. You have the input, random process. Here is the innovation, which is ID uniform. And here's the output after you train it perfectly, will match to the input. Okay? Now, the first question you would ask is, all right, you are not guaranteed this thing can recover the input. Do you lose information by using innovation? Who knows? You're doing all these operations, some information might get lost. Okay. Is there a loss of using this rather than the original data? Okay. The answer is no for this case. Okay. So forecasting future distribution based on xt is the same as forecasting future based on this much simpler random process, which is IID. Uniform. Okay, so what should be these two things? You can probably expect what is going to happen. Okay, I have an autoencoder. I have the input up to time t star. And this encoder maps to a sequence of independent random variables from of infinite paths to t star. But because this innovation is independent of the future, all I need to do is just to generate IID unit. Okay, here you use the decoder. You can easily show that, in fact, if you take this, what the samples coming out of this decoder will be following exactly the same conditional distribution. Of course, training is assume everything is perfect. Okay, all right. So that tells you this is the structure. Okay, if you do this, if you can train this autoencoder, then the implementation of generative random forecasting simply reduces to generate realizations of a bunch of IID uniform samples. Each of these samples will produce a new realization of the future. Okay. All right. Now, how do we test something like this? So there are all kinds of algorithms. These are like many, many different algorithms to do forecasting. So I'm going to restrict myself to do the forecast of electricity prices. But the first question you would ask is, how do you measure probabilistic forecast? The problem is that you don't have a ground truth. You cannot really compare with the ground truth, which is the underlying distribution. You do have a sample. Okay, but you know what? But sample is not what we want. We want to measure how good is the probabilistic forecast. This is, in fact, is a somewhat open problem. There's no everybody agreed metric of how to evaluate probabilistic forecasting. One way to do is if you forecast distribution perfectly, then you must be able to compute the optimal point forecast. Okay, so that means that you can evaluate the point forecast performance. You take all different kind of point forecast performance, squared error, absolute error, all kinds of things. Now, if you happen to get the distribution perfectly, you should get these metrics perfectly, right? So that's not a very good way to look at this. There are other metrics to measure this. It is quite ad hoc, but it's somewhat intuitive. One is called the continuously ranked probability score. Okay, let me explain what this is. Suppose this is what you want to obtain. This is the conditional distribution, okay? And you get only one sample. You compare whether this sample is consistent with this distribution or not. Okay, I'm using this tilde here to represent you're going to do empirical evaluation of these expectations, right? So this is widely used. It seems to be the only one that everybody compare. So yeah, so these are, you take different samples, you run all these things. You test all these things. So this is averaged over all possible past realizations. This is also averaged over all the future sample you want to forecast. Okay. The other one is look at the coverage. You want to be able to narrow down your probability distribution of that sample, but it should not be unconditional one. It should be based on what you have observed. You can imagine that that information will make this coverage tighter by knowing the path, right? If you just unconditioned one, in general is much wider, right? All right, so here is the practical problem. Okay, so I'm interested in locational marginal price, which is in New York, in other places, that the electricity prices, the wholesale electricity prices, is produced every 5 minutes. Okay, every 5 minutes. You wonder how they compute the price. Now, the locational marginal price is computed through an optimization program. Okay? Here you're minimizing the total cost. Here is the generation limits. Here is the power balance. Here is all the transmission line. What is the limit of transmission line? You solve these, most time linear program, you get the Lagrange multipliers of power balance and power flow constraints. That's what it is. Okay. Now, this should tell you why this thing is quite difficult to forecast. The reason is this inequality constraints. Whenever the inequality constraint is not binding, that thing equal to 0. This thing equal to 0. You don't have this term. The moment it's binding, it's at this thing. So this the reason that the locational marginal prices of electricity has these big spikes. Okay. From non-binding to binding, it can be a very small change, then all of a sudden you add a huge number to it. It's very difficult to forecast. Okay, so that's a realization of New York electricity prices. You can see this huge jump from 100 to 600, and so on. Quite a big variation, very spiky. Okay, of course. So here is the locational marginal prices of Long Island bus. Of course, you can other information you can use, right? So in forecast problem, I'm going to assume that this is the current time, this is the information you have, and you are interested in something 1 hour ahead or 2 hour ahead, a period that you are interested in what these prices are. Why you're interested in that? Because you're gonna try to arbitrage with your battery or something like that. Okay. So given every information here, you want to forecast 1 hour ahead what will be the real-time prices. Okay. Now, you can use other information. Your day-ahead electricity price is already available to you in real time. And you can take the load, what is the demand like. That is also provided by ISO. The operator would tell you what the current load is. And you can also use neighboring prices, okay, to help you to forecast something like this. All right. Okay, this is messy. You're gonna have to evaluate all kinds of. So we're evaluating first all the point forecast metrics. Ideally, if you're perfect, you should be doing well in all of them. Okay. All these are probabilistic forecasting measures, and these are what we are doing. We're not the bold-phase one is the best. Okay, the bold-phase one is best. Sometimes the best. So second is the second rank, right? So these numbers are ranking. We're close. We're not doing as well in the point forecast metrics. These are the probabilistic forecast metrics. Okay. This is intuitive for each season: the summer, the fall, the winter, and so on. This doesn't tell you what the inside is. Okay. Here are the trajectories, forecasting trajectories. Okay. So the way you produce these forecast value, for example, here, okay, is that you generate many samples, and you take the conditional mean if your metric is mean squared error, right? If your metric is absolute error, you should take the conditional median. So that's how we compute all these points. We can forecast this, but you have to generate so many that to capture something like this is a very big deviations. All right, I think I'm almost running out of time. Yeah, so I don't have a chance to talk about the next interesting problem of detection. Let me just mention what is this about. So this is about detecting anomalies. So this is a big event in California when there is wildfire. And these are subtle changes in the waveform, okay? And what happens is that all these solar farms, when they have these kind of jitters, think that there is something bad happens. They would look at the detector and say, is it an anomaly or not? If it decides it's to be an anomaly, they will back off, because that's the way to protect your solar farm. Now, one farm backed off triggers other farm back off, because what those are when they, before they back off, they produce power. Now they back off, then you immediately have imbalance, and that triggers a cascade back off of 1.2 gigawatt loss. Okay. Anyway, so the problem is that these are time series. You have measurements of the voltage and currents. How do you detect such anomaly? Okay, so I won't say much about how to do that. Let me just go to here's some really interesting way to do this. I think the detector is invented by Niemann in 37. It is also, interestingly, has a neural network architecture. You can call this a kernel-based neural network. All right. Okay. So let me just conclude. I think the essential characteristic of foundation model is you have to have this latent process that can be used generically for many applications. Okay. So for Cypress physical system application, the time series innovation is what I consider a correct way to represent. Okay, so we need to produce latent features. So I think that the innovation representation, rather than large language model, which capture different characteristics, is the correct one. Yeah. Of course, in practice, you're going to incorporate other types. So I'm going to stop here.
Great, thank you. Very pedagogical, very interesting. So the floor is open for questions. Yes?
Thank you, Professor. I have a question about matter of size. So as we know, the data that we take is enormous in terms of size. So what about latent feature? How large is that? So
You can, one important thing is the foundation model. You train with normal data. Okay, you train existing. So power system, these things measure these very quickly. Measurements is 14 kilohertz per second. It's like 14,000 per second, right? These are data that are stored years. Even the price data, you can get a clean price data go back for many years. So if you ask how big it is, yeah, there are lots of them.
Comparing the latent feature to the data that you take, do we?
You do not have a reduction of dimension. However, you have a reduction of description. To describe arbitrarily dependent time series, you need all possible joint distributions. Here, single one, because they are totally coupling is removed. Right? So it removes all possible coupling. So, but you don't have a reduction in dimension.
Thank you for the presentation, Professor. I'm actually curious about the input data itself. How would you think about the input, how the input data would actually affect the eventual output? Like, did you do any sensitivity in terms of determining what would be the best?
No, we just take the data.
So any data,
you just take the price. In this case, you just take the price data. You can go to New York ISO, any ISO. Price data is there. We don't do anything. Of course, you can use many different locations. That's not what we are doing. We just used Long Island measurements, their neighboring New York City measurements, some load data measurement. In fact, we construct our network is quite small. It's not even that large. And also, these surprise data is actually not that does not have long-range dependencies. If you really implement, large language model, they try to capture really long-term dependencies. It's very difficult to train, but this one is pretty easy actually.
My other question. Oh, there's one there. Sorry, I didn't see.
Thank you, Professor. I'm curious how the physical laws are captured in the foundation model.
Right. It captured because it is collected from physical system.
Because of the time series data?
Because the data is from there. I think it is a different kind of principle in modern AI training. You don't write particular constraints into your optimization to enforce that. The belief is that everything is in the data. If you have large enough, it will learn it, right? So even I think in ChatGPT you don't write the program books in. It's simply you have overwhelmingly large training samples, right? So it is only physics because the data come from physical system. We don't really check whether write something in the training you have to enforce Kirchhoff law or something. That would make these kind of training much more complicated.
But what if a system requires high reliability and you want to perform the decision making?
That's a different question. Here, you have the forecast. If you want to make the system more reliable, maybe you can use the forecast to do better job. This is not a part of the design yet. I'm just talking about forecast, right?
That was my question, but I've got another one. So if I wanted to predict price spikes, I would like to know what the offer stack is. You have that. I mean, those data exist. The guys in the system, I may not make it public. Right?
So my question is, if you are just interested in price spikes, which means that you are interested not just samples follow the distribution, you are interested in samples that are actually extreme. Now, I can generate as many samples as you want. I can create those really rare event samples. Because this doesn't require anything else, you just run random generator, right? So what I imagine will happen is you do something like this, and you can have other predictors that try to use samples that are extreme, top 1% samples. Okay, what does it look like? Where does it fall, right? That is entirely easily implemented here. I can give you two.
Well, when we tried to predict price spikes, basically the key thing was what was the error in the load forecast. So if the load was sort of higher than you had planned, then the probability of a price spike was substantially higher.
We haven't done anything sophisticated at all.
Not yet.
Not yet.
I think it was,
Following off of Tom's question about the data driving something physical and neural network. So, I mean, your physical system is changing though. For instance, your anomaly, when you had the solar plants turning off, where you're having periods of data then where you're adding new solar to the causal system. So, how does that impact the neural network?
I don't know. Theory doesn't work. Non-stationary case, I don't know how to deal with it. We tried seasonal, so we do the forecast based on each season. We train them differently. You have to have a trade-off between how much data is available for you to train, if you believe these things changing all the time. I don't know. There are a lot of things. Training is like really a black art. So that's why my students get paid so much not for the theory, for sure.
I think there was one short question to
Yeah.
finish.
So the price spikes, I guess, so you predict a point forecast and then you solve optimization problem that will give you the price.
Yeah.
Have you or anybody else has used like the marginal prices, like Lagrange multipliers?
That's all those prices are computed from that. That's exactly how ISO compute
So for
prices.
the next one, do you use the marginal price here to forecast or not?
No, in the forecast, you only use the past. Past plus neural network, that's it. Now, these prices are computed by operator using the Lagrange multiplier.
But you
I don't
have
do
access-
it.
You don't have access to that.
We
You
don't.
have to the-
Yeah, we only have price. We don't have anything else.
Thank you.
Yeah. If you know that program, then it's a different story.
Thank you. Thank you
Thank
very
you.
much. Let's